to share a little bit about the Aurora. I'm a space physics PhD student up here in Fairbanks, a little bit further north than where you all are at. And we see auroras here quite frequently. So it's a nice place to go to school and study this stuff, study space weather, because we can kind of see the direct effects of it. So over the course of the next 45 minutes, I'll tell you a little bit about how the auroras are formed, how you can plan a trip up to Alaska, and how you might actually be able to see the northern lights from your latitude and maybe even from your own backyard. So the title of my presentation is Chasing the Aurora, Nature's Most Spectacular Light Show. And I'll start off with a little bit about myself, and then I'll jump right into space weather and aurora science. I'll talk about when the sun gets angry and how auroras can be seen all across the lower 48, as they were just a couple weeks ago. I'll give you some aurora forecasting tips and tricks and talk about aurora photography and time lapse. Then if we have time at the end, I'll show you some of my favorite aurora photos, some recent ones too from this past 2025 season. So, yes, people like to call me the Aurora guy. It was not a name that I necessarily chose. It was just, one night somebody came up to me and asked if I was the Aurora guy because I was posting photos that just on Instagram. I was going to school in North Dakota. That's like where I cut my teeth chasing the Aurora. I'm originally from Minnesota, used to the cold. And they asked if I was the Aurora guy. I said, I don't know, maybe. And all my friends said, no, you should just embrace it. You should just call yourself this because this is all you do. And it's true. I'm like kind of obsessed with the Aurora. I saw it for the first time when I was 4 years old. Back in 2003, there were some really strong storms and just became fascinated with the night sky after that. I was in Boy Scouts. I went camping a lot with my dad and with my parents. And in Scouts, I picked up a camera when I was 15 years old and started taking photos of the night sky. And then one thing led to another. And here I am up in Alaska doing my PhD in this stuff. So I would consider myself a professional aurora chaser. I have a tour company now and lead workshops and all that. And I've probably seen the aurora, I don't know how many times, 200 or 300 times. I'm also an intern at the Aerospace Corporation down in Los Angeles during the summer. And so I've spent the last 3 summers down there and also really passionate about citizen science and science communication. So believe it or not, all of you in the room tonight can become, real players in the research community, in the Aurora research community by submitting your photos and sharing with scientists what you've seen in the night sky. It's really, really cool. And I've been on a lot of aurora chasing adventures. This was one of my first big trips that I took. This was Churchill, Manitoba in March of 2022. And you can tell it's 2022 because we all have the masks on. This was, during the tail end of COVID, taking the train from Thompson, Manitoba up to Churchill. So that's the Hudson Bay you're seeing on the left, looking out into the vast expanse of ice. And yeah, there are these things called polar bears that will try and hunt you while you're out taking photos. This was a really fun trip. And then I went back in September and actually saw polar bears. In March, they're mostly on the ice, but in September, they're on land because the Hudson Bay is not frozen yet. And, it's one thing worrying about bears and moose when you're out in Alaska, but polar bears are just another story altogether. So I snapped these photos of polar bears, and the rightmost one is is really the most scary one because this one was out while we were aurora chasing. So, when you're seeing this on the side of the road, you think that you're safe, and then all of a sudden you get in the car, moving to the next location, you see one of these guys, and that's a little bit unnerving. This was one of my most seminal moments under the aurora, like my first high latitude substorm. So the left-hand side is showing a video of the right, and this was when I was up in Fort Yukon, Alaska, helping out with a sounding rocket mission. So to study the aurora, scientists use sounding rockets instead of, flying a satellite through or launching a weather balloon because the aurora occurs at an altitude that is too high for weather balloons and too low for satellites. So you have to launch rockets through to actually sample the aurora where it's occurring. So I was up in Fort Yukon running some cameras and saw this amazing, it's called a substorm, saw this amazing substorm and this huge auroral spiral. And that really convinced me that I needed to move up to Alaska and get a PhD in this stuff. It was just so life-changing. So those are some of my most memorable Aurora experiences. I've had a lot more than that. I've been to Iceland. I've seen the Aurora in India. I'm actually going to be helping out with another sounding rocket this coming year, spending probably a month up in the middle of nowhere in a little trapper's cabin, with a bunch of camera gear. So it's really fun time being a student, and very grateful that I'm up here in Alaska able to do what I'm doing. But let's talk about space weather, and let's kind of kick right into gear into what the aurora actually is. So, in order to figure out what the aurora is, we have to zoom out and talk about what's called space weather. So, a lot of you, well, I hope all of you know what terrestrial weather is, right? You have rain and clouds, wind, all that stuff we experience on the ground. Well, there are similar phenomena, analogous phenomena in space. And the science definition of space weather refers to conditions around a star, like our sun, and its interplanetary space that may affect space and ground-based assets as well as human life. So what's important about space weather is that it does affect humans. This is one of the reasons why I wanted to join this field and go into this field of study, is that, what I'm doing and the research I'm doing has a direct benefit to humanity. But really, that might sound complicated, but you can boil down space weather into the aurora. The aurora is probably the only bit of space weather that we can really interact with and see with our own eyes. Everything else comes from observations in space, or they're, concepts bounded by magnetic fields and, sort of invisible phenomena that we can't really interact with. So that's why I love the aurora, because it's one of these things where you can talk about space weather and then point to the sky and say, hey, here's what I'm talking about. Here's the final step of this entire interaction from the sun to the earth. But of course, it's not just aurora. We have solar flares. We have coronal mass ejections. We have, giant shock waves. We have million-degree plasmas. It's a really diverse field, and it involves a lot of different disciplines, from auroral physicists to engineers to biologists to policymakers. Space weather is a really complex and diverse enterprise that involves not just researchers, but forecasters and also industry partners to make sure that all of us are being protected by these hazards in space. Everything starts with the sun. Just like we have weather here on Earth, as I mentioned, the sun also creates weather in space. And most of this comes from the solar wind. It's this, I kind of like to make this analogy where you think of a hot cup of coffee and you have the steam that rises off the top. That steam is kind of like the solar wind, and the hot, warm liquid inside the cup, the coffee, is like the sun. This solar wind just kind of flows out. It's like the extension of the sun's corona, or the outermost layer of the atmosphere, and bathes everything in the solar system in this supersonic breeze of charged particles. So the sun also is dynamic and constantly changing. Obviously, when we experience the sun here on the ground, we just see it rise and set. We don't really think twice about it. It's there, it's always there. But when you actually look in space with special telescopes that can see in different wavelengths, you can see that the sun has a lot going on. And this kind of controls the solar wind, which usually is calm and gentle, but this activity on the sun can make that solar wind either really fast, it can cause big gusts of solar wind, which we call coronal mass ejections. And this solar wind transports energy from the sun out into the solar system. And we'll learn about how that energy from the sun interacts with Earth and its magnetic field, producing auroras. But this is just a cool video I like to show, just illustrating the fact that the sun is always changing. This is just over the course of a couple hours, seeing this huge, chunk of the sun's atmosphere being blown off in what's called a coronal mass ejection. It's like a giant sun burp or a sun sneeze, just launching, billions and billions of tons of plasma out into space. And sometimes these are directed at Earth and can transport large amounts of energy, into space, and eventually interact with Earth's magnetic field, causing things like geomagnetic storms. So people are monitoring the sun all the time for these explosions, these CMEs, along with other phenomena. To not only understand when we might get more auroras here on Earth, but also if there's any other impacts on society. So this energy from the sun, doesn't just hit Earth and go right down to the ground, right? Well, we first have an atmosphere that protects us, but then if you've, ever used a compass, I'm sure all of you use a compass. My generation, I don't think so. You have a compass that points north, right? Earth has a magnetic field. We all know this. It's why, we have maps that work in our phone. Phones have compasses in them. And this magnetic field doesn't just stop at the ground. It extends into the atmosphere, and it also extends into space and forms this protective bubble around us called Earth's magnetosphere. And in a perfect, pristine environment with no solar wind, it would just form this perfect, circular kind of, or I should say spherical bubble. But because there's solar wind that's pushing up against Earth's day side, it causes that part to be compressed, and it extends out the night side, which results in this sort of shape like a comet's tail. And so that's what gives us this magnetosphere, which if I pause this video, you can see the solar wind is coming here from the right-hand side of the screen and then impacting Earth's magnetosphere and pushing it. And a lot of times, or I should say most of the time, the solar wind and the energy in the solar wind just sort of gets deflected around Earth's magnetosphere, kind of like a rock in a stream of water. But under the right conditions and the right magnetic field orientations, that energy from the solar wind can penetrate in down, flowing along Earth's magnetic field lines, kind of to the weak points of our magnetic field, which are over the north and south poles. Then that energy goes down, funnels into the atmosphere, and eventually creates the aurora that we see. And so auroras are created in Earth's ionosphere. Here's a little cartoon showing the different layers of Earth's atmosphere down from the troposphere here close to the ground. That's where we spend, unless you're Felix Baumgartner of Red Bull, you're probably not going into the stratosphere. Even commercial airlines kind of top out at the top edge of the troposphere. So all of life on Earth and the weather that we experience happens in the troposphere, but there's a lot more to the atmosphere than just that. And if you go higher and higher, you eventually get to regions which are not just, O2 and N2, which we breathe here on the ground, but also charged particles and these molecules that have separated out into what we call the ionosphere. So that prefix iono corresponds to it being charged. So we have charged particles flowing around in Earth's upper atmosphere. When we have particles from Earth's magnetosphere, from outer space, which are usually electrons, coming in along Earth's magnetic field lines, they're encountering these gases in Earth's upper atmosphere, and these charged particles can interact, creating chemical reactions which produce light. And just to back up a little bit, this is way higher than planes fly, of course, also way higher than all terrestrial weather. So it's really important is that if you want to go aurora chasing, you need clear skies. We all know that from just taking photos of the stars and the Milky Way. You can essentially assume that the aurora occurs at the same point as the Milky Way. You need clear skies and all that. So that's you would assume that's common knowledge, but a lot of people when they get up to Fairbanks think that the auroras are just clouds. So if it's cloudy, it's fine because it's just more clouds. No, it's way higher than all the weather that we experience. And I kind of already talked about this, but the different colors of the aurora are produced at different altitudes and by different gases reacting with these electrons from outer space. So as an electron, let's say, is traveling down Earth's magnetic field line, it's like a surfer riding on a wave. It starts encountering Earth's atmosphere maybe around 120 miles in altitude. And the first thing that it encounters is atomic oxygen. So as it deposits some of its energy, it's kind of like a game of Plinko. It's just boom, 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 boom on all these particles as it's making its way through until it loses all of its energy and then eventually just sort of dissipates. But the first kind of atomic species it encounters is oxygen that can glow red. And then as it goes further into Earth's atmosphere, the density increases. We get different kinds of gas. We get nitrogen. We get different kinds of oxygen, and we can get blues and greens. And then if that particle, that electron's really intense, it has a really high energy, it'll make it all the way down and create nitrogen, that N2, we like to call it a nitrogen fringe at the very bottom of the aurora below about 60 miles in altitude. So that's kind of like akin to rain that we experience here on Earth. It comes from clouds, and it's kind of the same thing. Scientists call it particle precipitation. And the different shapes of the aurora, that's a little bit harder to pin down and why that occurs. But you can think about the different shapes of the aurora from the different kind of clouds of plasma and different sort of magnetic field configurations in outer space. So the reason why we even study the aurora in the first place is that it's a way to actually visualize the different processes going on in Earth's magnetosphere that are otherwise invisible, because it's just magnetic field lines and electric fields and particles, which we can't actually see until they deposit down in the atmosphere and create the aurora. So it's like the magnetosphere is painting a picture. The paintbrush is Earth's magnetic field line, and the paint is the aurora in Earth's upper atmosphere. And also, you can think about it like a giant neon lamp, except for the electricity is coming from outer space instead of a 120-volt wall outlet. And here are some rare auroral colors. You can get different mixtures of reds and greens and blues, and you can get purple and orange and all sorts of different colors. And when we see geomagnetic storms and kind of enhanced space weather, we typically just see wilder and wilder colors. These are a few of my favorites that I photographed from up here in Alaska. Now, the aurora occurs somewhere on Earth at every single time of the day, every single day of the week. And statistically around these two sort of donut-shaped areas called the aurora ovals over Earth's north and south poles, aurora borealis and aurora australis. And the reason why this happens is because Earth's magnetic field, the sort of weak points are at the north and south poles. So under quiet conditions, the aurora ovals just sort of hang out there because that's where all the energy from the solar wind is flowing down over Earth's, I should say, into Earth's magnetosphere, along the magnetic fields kind of congregating over those polar regions. So if you want to travel and see the aurora, you want to go to somewhere around these, or I should say underneath these aurora ovals, places like Fairbanks or Iceland or Tromsø in Norway. You can see here these two models. This is the Ovation Prime model, and you can see this is kind of enhanced a little bit, but this aurora oval, and it's centered around Earth's geomagnetic poles, so not the geographic poles. So actually us here in North America, we're favored a little bit over places like Russia and Siberia because the geomagnetic poles tilted a little bit towards us. Now we have the aurora ovals, which are, always there in some capacity. If you've ever been up to Alaska or any high latitude place, or you've seen the aurora from where you're living now, you've probably noticed that it's not the same all the time. The aurora often goes through these cycles, which we call substorms. And what happens is the aurora can kind of charge up, the energy in Earth's magnetic field can grow, and then all of a sudden be released, like you're pulling back a rubber band, and there's a slingshot of aurora particles that just light up the sky. So there's different phases of auroral substorms. There's the growth phase, where the aurora kind of is charging up. This is kind of from the perspective of the high latitude observer. So us here in Fairbanks will see these auroral arcs moving across the sky towards the south. And then all of a sudden, over 1 to 2 minutes, you get these little fingers of aurora called auroral beads that form, and the aurora then slingshots back north in the expansion phase. Then after that, the recovery period means that the aurora needs some time to breathe, take a little bit of a breather, and there's usually 1 to 2 substorms per night. So this is a fundamental process of Earth's magnetosphere, this loading and unloading of energy, which occurs multiple times per day. And these space weather phenomena, even though they're beautiful with the aurora, can also cause issues for satellites because you have a lot more particles all at once being deposited in Earth's atmosphere. So if you're a satellite, it's like you're a big, it's like you're flying in a plane and you fly into a huge rainstorm, right? That can cause some issues. And also these intense currents in Earth's atmosphere can create intense currents in Earth's surface through Faraday's law and the induction, and can create geomagnetically induced currents which flow up through power lines. It can cause blackouts if the substorms are strong enough. So although they're really pretty, they're an area of research, and we want to understand how they form and why they happen. And that's actually somewhat what my PhD thesis is focused on, is why these substorms kick off and what causes them. But what causes auroras to be seen at mid-latitudes? There were auroras in Arizona, New Mexico, California, Texas a couple of weeks ago. Why does that happen? Well, the sun can get angry, right? I talked about this, gentle breeze of solar wind. Well, it can turn into a giant storm, solar storm, as people call it, due to things like coronal mass ejections, also coronal holes. I'll be talking more about CMEs because they can cause the largest kinds of geomagnetic storms, but there's also coronal holes, which are sort of these areas of open magnetic fields on the sun, which stream out this fast solar wind. But for all intents and purposes, if you're trying to see the aurora, down in the mid latitudes in the central US, you want to watch for CMEs. They're like these big burps of plasma from the sun, and we can actually see them happening if we block out the sun with a little occulting disk and
Oh, no.
We freeze totally?
they might be going in the solar system, and if they're going to be interacting with Earth, if they'll cause geomagnetic storms. And so, yes, we can predict them. You can see here on the left a popular model. It's called the Enlil model, Enlil. It's used by many different space weather forecasting agencies. And this big spike right here is the CME impacting Earth. So you're kind of like in the frame of the Earth. And agencies like the NOAA Space Weather Prediction Center will put out news releases and information about incoming coronal mass ejections that you then can use to figure out when conditions might be good for enhanced geomagnetic activity, and those auroral ovals to then expand down to lower latitudes so you can see the aurora from your location. And there's been some talk. I mean, every single year it seems like the next year is the year to go and plan a trip, or you have to see the aurora before it dies or something. There's a lot of hype, but the aurora is slightly stronger right now. Just statistically speaking, there's more of these coronal mass ejections and coronal holes to pump up geomagnetic activity and cause the auroras to be seen from areas further away from the normal auroral ovals. That's because we're at solar maximum. So if there's any ham radio operators in the room, I'm sure you already know about this, but we're kind of on the declining phase of solar cycle 25. Right here is an arrow kind of pointing to where we're at. This is a plot of sunspot number over time, and you can see we bottomed out in around 2020, and we're now kind of over the hump, declining to where we may see solar minimum conditions again in like 2030. But right now is a really good time to be an aurora chaser because there's a lot of space weather activity, and this current solar cycle is actually outperforming expectations by like 50 to 70%. So we've had some good storms. If you remember the storm last year, almost a year ago, in October, as well as the May 10th, 2024 storm. We've had some nice activity and there's just more opportunity. And so, yeah, now is a great time to be an aurora chaser. I should also mention that the auroras do not disappear at high latitudes during solar minimum. We still have the aurora ovals, which are always there. So if you're thinking about planning a trip, you don't need to plan it in the next, 2 months. You have many, many years to do that. So we can predict the aurora kind of, but one thing to be aware of is the KP index. I like to say that if you're trying to predict when a tornado is going to hit your house, knowing what the global cloudiness index is not going to help. And that's kind of what the KP index tells you, is just how active globally is Earth geomagnetically. So if it's a 1, then it's supposedly quiet. If it's a 9, then we classify that as an extreme storm. Anything above a KP5 classifies as a geomagnetic storm. But KP is problematic because it's one value from 1 to 9 that's attempting to characterize, if you're using it for auroral visibility, attempting to characterize something which is very spatially localized, which means that you can have a substorm which just kind of lights up one portion of the auroral oval and leaves everything else totally alone. Just like if it's a really high severe weather day, you might just have one supercell that dominates everything. You might get an EF5 tornado from that, but then the rest of the county is completely dry, right? So there's no way to tell when the aurora is going to be really good or when you might see the aurora by just one number that characterizes the entire globe. It's just not meant for that. So the KP index, the reason why it's used is because it's a historical measure and it does relate to just overall Earth's geomagnetic activity, but not necessarily what the aurora is doing. So what I like to use instead are webcams, social media, or online sites like aurorasource.org. Really just anything where I can get a more real-time picture of what the aurora is doing and have some eyes actually looking at the sky and telling me, hey, there is an aurora happening now from this location, versus some number trying to tell me that. So webcams are my favorite resources. This is one up in Alaska that's really close to the university. So, I live in Fairbanks, so I use this all the time at night. But essentially, if you're seeing aurora on a webcam and that webcam is near your location, then you can see it as well because the aurora is really high up in the sky. So just like seeing a thunderstorm way out on the horizon, hundreds of miles away, the same features in the aurora can be seen from all across the US. In fact, I've been on the phone with one of my friends who is like 5 hours away. We were looking at the exact same auroral display, and we both saw this one pillar of aurora that was just shooting in the sky, and we were on the phone and remarked about it at the same time. And it's crazy. I mean, we saw the exact same aurora. So people have this misconception as well that you need to be in a certain city or even like a certain parking lot or like a certain resort to see the aurora. No, it's out for everybody if it's out. So there is some spatial localization with the substorms, but that's more on like a hundreds, to few 100 mile scale size. So this is just a nice time lapse here. This is an all sky camera. If you're not familiar with this kind of view, it's a circle image, but it's showing a 180-degree field of view of the night sky. And that's really common for these webcams. So I'm not going to get into all this like in depth. I have a lot of information on my site, but instead of the KP index, we can use a bunch of different metrics, proxy measures for auroral activity, like the GOES magnetometers. That's my favorite. Auroral electrojet indices, real-time solar wind, the Ovation Prime model, and I already talked about the Enlil model to forecast CMEs and solar wind enhancements. Talking about Enlil, you can see here I've annotated this graphic here on the right. This is a model run of a CME that happened last year. and it gave us a nice aurora, and we kind of got clipped by it. As you can see here in the model, it was fairly accurate. These models are not 100%, right? There's always uncertainty, and that's not necessarily communicated by the agencies like NOAA and NASA, but it's something to keep in mind is that if you see a CME is going to impact Earth, it really is that time plus or minus 7 to 10 hours. So this is nice because it gives you different views. You can see a top-down view here where the sun's in the center, Earth is at the right, a side view showing you, how inclined relative to the ecliptic the CME might be if it's heading south or north of the Earth. And then this is the in-plane kind of impact footprint on the very right here. I almost never use this, but Enlil is really nice. It can show you CMEs and coronal hole high-speed streams. And if you're down, at low latitudes, this is what you want to pay attention to. And these, different solar storms that can really pump up activity and cause geomagnetic storms, causing the aurora ovals to expand to lower latitudes, giving you a chance to see the northern lights. One model that's doing the same thing, just in a different format, is the Huxt model. I have a blog post about this. You'll see in this presentation, I've sprinkled some links in here. Don't worry, because at the end, I have a QR code that you can use to scan and download this presentation. I've uploaded it to a website as a PDF and PowerPoint file. So if you want to, take notes, you don't have to be so frantic. This presentation is available right after this. So this is kind of nice. It shows a big spike, as you can imagine, from a CME forecasted to hit Earth. And the KP index I already mentioned is not the best measure of geomagnetic activity. One example, or I should say one sort of supporting piece of evidence, is that the magnetometers, so the measurements, like the stations that measure the KP index, are not even under the auroral oval. So especially when you're up at high latitudes, the KP index is not helpful because it's measuring magnetic sort of changes in Earth's surface caused by the aurora overhead. But if the aurora is not overhead those magnetometers, it's just not going to record anything. So here on the right, you can see a distribution of the KP observatories. You can see there's also a big bias in Europe. So if North America has aurora and there's nothing in Europe, the KP index may not respond, as sort of immediately as if that aurora was more centered over the European sector. So again, I'm not going to sort of grade on this for too long. I'm just not a fan of the KP index, as you can see. But there's a lot of things that use it, right? And my most favorite and probably the most funny thing is going to Chena Hot Springs near Fairbanks. It's a pretty touristy area, so they just list the KP index as, the thing to watch on the whiteboard when you walk into the hot springs. And to make things even simpler now, they just call it the Aurora Activity Index, which is even worse because nobody knows what that is. So yeah, it gets baked into everything, including your favorite Aurora chasing app. It gets put into view lines. The news will report about the KP index and say that you need to see, or you need to be at a KP 7 to see the Aurora in Colorado, when we've seen big substorms that push, that push auroral visibility down to that same latitude, and it's a KP 2 or 3, right? The KP is also measured every 3 hours, which is a big problem because substorms can last 15 to 30 minutes sometimes, or even less. So, if you're trying to capture that brief, really intense burst of auroral activity, a 3-hour measurement is just going to smooth that completely over. Or it's going to come in, it might be a KP7, but it might come an hour and a half after the substorm's already happened. So there's been so many times when people will say, oh my gosh, it's a KP7, I'm going to go outside. And it's in the recovery phase, and the aurora is almost dead. There's nothing happening because they missed the substorm because they were just chasing off the KP index. So I've already talked about this. Yeah, also KP predictions are more like best guesses. Space weather is really hard. We do the best that we can, but we can't really predict the KP with any degree of accuracy, especially when it's quiet times. Beyond, we just really can't predict it at all. So if you see a three-day KP forecast, just take that with a grain of salt. The auroral electrojet index measures global auroral activity. So it's kind of like the KP index, in which it's an averaged metric over many magnetometer stations, but it's coming from a chain that's underneath the auroral oval. So it's more translating to the actual auroral activity. And I always tell people this is sort of like the next best thing to KP if you're just wanting one number to tell you whether to go out or not. And, for the central US, I always say around 1,000 nanotesla to 1,500 is kind of what you quote unquote need to see aurora. But this also has its limitations. So just keep that in mind. I mean, nothing is perfect, right? Obviously, going outside and actually looking yourself is the best way to know if there's aurora or not. But we want to save ourselves the time and actually have some sort of forecast or way to monitor things. So the AE index is getting a little bit better. Real-time solar wind is even better than that. So watch out for negative BZ. That's what gets the substorms to charge up and allows Earth's magnetic field to connect with the solar wind magnetic field and that energy to transfer into Earth's magnetosphere, excuse me, and penetrate down into the auroral ovals. And there's some research that shows that substorms in the expansion phase, when the aurora gets really, really bright and vibrant and dances around, those are triggered by BZ turnings. So if you see a really sharp turn from BZ south or negative to north, that can trigger one of these big eruptions of aurora. I have an ebook that goes into a lot of details about the solar wind and how to read these charts. Obviously, you can't cram everything into 1 hour, let alone 45 minutes or, even into like a week-long course. But you can get a sort of flavor of all this in this free ebook. And yeah, again, it's free. So feel free to scan the QR code and download it. I think it's a pretty good resource. I'm working on a next version as well. The Ovation Prime model kind of takes in the solar wind data and gives you a model auroral oval. It's really nice because it's a pretty friendly graphic. You can see it literally looks like the auroral oval. So people use it all the time. But what's important to note is that it's just a model. So it cannot forecast substorms. It's based on statistical empirical data. So, it's smoothing over a lot of the variations that we want to see in the aurora and these substorms that we want to capture. So it's nice and it gives you sort of an idea of what's happening. But again, know the limitations and keep that in mind when you're using this product. So yeah, to forecast auroral substorms, again, just to recap, it's 15 to 30 minutes of really good auroral activity. When the substorm happens, if you're directly underneath, you're going to see the aurora dancing and just swirling all over the place. If you're far away from the aurora, and this is how you can see the aurora from states like Arizona, California, Colorado, what's going to happen is there's just going to be so many more particles flowing into Earth's atmosphere. It basically causes the aurora to become really, really tall. So imagine like the aurora is just like this sort of static band across the sky. All of a sudden it grows to maybe 500, even, 1,000 kilometers in height. And because you can see, like, for example, a thunderstorm hundreds of miles away, just imagine if that thunderstorm was 100 miles tall. You could see that probably from 1,000 miles away, right? It's the same thing with the aurora. When that aurora becomes really tall and really bright, all of a sudden places further away can see that. And it might just show up as like a red glow to the north for you because the Earth's curvature is blocking the green, right? The green occurs below the red. It's there. It's just that the Earth's curvature is blocking it out. So that's why we want to really forecast these substorms, not just being in Alaska, but also at mid latitudes. That's really what you're trying to watch for, is these sudden bursts of auroral activity, which you can detect, maybe not with your eyes, but certainly with a long exposure facing north. And so one of my favorite tools is the GOES magnetometer. Of course, like I said before, this is just a crash course. If you're confused or this is like drinking from a fire hose, feel free to ask me questions after this or send me an email. But essentially what happens is as you have BZ south, so this is, again, the Earth's magnetic field connecting with the solar wind, it's basically peeling back Earth's magnetosphere into a really, really narrow comet-like tail. It's like you're taking this rubber band and you're pulling it out really, really far. The actual shape of Earth's magnetic field then is really compressed. It's really short. And you can see that in this plot called the GOES magnetometer. It measures sort of like the height of Earth's magnetic field. So as it gets pulled out, it gets shorter and shorter and shorter. Those graphs dip down. All of a sudden, when that rubber band releases, when the tension gets too, high, Earth's magnetosphere just can't take it anymore. That rubber band shoots out and becomes more of like a circle. It becomes more dipolar, as we call it. And the graphs shoot up. And that corresponds to one of these substorms happening. And these graphs correspond really well to intensifications in the aurora. It's hard to see, but what I've done here is taken an all-sky camera time lapse and overlaid it with the GOES magnetometer plots on the bottom, and there's a green bar indicating the time. I'll fast forward a little bit so you can see that when we have a shoot up in that graph, when we have the GOES magnetometer plot spiking, you see the aurora immediately after intensify. So this is a really good way to not only monitor whether or not a substorm is charging up, but also you can see in real time when one of these big injections of energy is coming from Earth's magnetosphere down into the aurora. So this is what I use every night. Up here in Alaska, I just use GOES magnetometers and webcams. All right, but like I said before, best way of knowing if the aurora's out is having somebody on the ground actually taking a photo of it and posting about it online. So that means you guys, ground truth data. If you want to report whether you've seen the aurora, there's a great site, aurorasaurus.org. It's a NASA citizen science project, and it's super nice because people will submit yes or no, whether or not they've seen the aurora sightings on this map. It gets plotted along with the Ovation Prime model, and you can see in real time where people are seeing the northern lights. Also, there's a whole science story behind this. If you upload your photos and your reports, those get used for science, and you can become a collaborator on projects and things like that. There's a lot going on here that I could talk about. Aurora webcams, I actually just updated my site today with a few more webcams I found in Canada and Alaska. I usually just have like 10 or 15 of these things pulled up throughout the day, just kind of checking what's going on. And this is kind of cool, but during the October storm last year, you could actually see the auroral oval sandwiched between these two all-sky cameras. The top one was in Maine, and the bottom one was in Georgia. I just thought this was a cool example of kind of what you can do with webcams and see physically where the auroral oval is laying out. There's forecasts on many different timescales, and what I'll just say here is that as you get closer and closer to real time, those forecasts tend to get more accurate. You have forecasts all the way, on the 27-day time scale, but then you also have solar wind and the GOES magnetometers, which can read essentially real-time, measurements of the solar wind and what's happening in Earth's magnetosphere. So just keep in mind that as you go out to like the 1 to 3 day forecast and the 27-day forecasts, those are more just like best guesses. It's kind of like throwing darts at a wall and seeing what sticks. But then as you get closer and closer to real time, those forecasts and what you can do with the data and what you as an aurora chaser can do to interpret the data can be more beneficial to actually forecasting what's going to happen with the aurora. All right, so moving through here to aurora chasing tips and tricks. Just a quick reminder, all of you can become an aurora chaser. It's pretty easy, relatively speaking, even if you forget everything in this presentation. I always tell people who are visiting Fairbanks, just stay up really, really late, drink a bunch of coffee, put out a lawn chair and stay up, look at the night sky, and you're going to see everything happening, right? All you need is some patience and a love for the night sky, and you're good to go. Obviously, if you're down in the southern US, you need a little bit more, you have some ingredients that need to come into place, like a geomagnetic storm or some sort of solar wind enhancement. But still, when there's some activity happening, you just got to stay up all night. And I'm sure that's not an issue for all of you. This is an astronomy club, but that's always the big, that's always the big struggle with people coming up to Fairbanks is that everybody goes to sleep too early. All you need to do is just look up at the night sky. It's that simple. Obviously, that works in Alaska. Down in mid-latitudes, again, you need some sort of geomagnetic activity. You also have more people to worry about. This is just an example here using Atlanta. So I showed a webcam screenshot from Georgia. So you can see the aurora from Atlanta, but you definitely don't want to go south of Atlanta to see the aurora happening north. So you need to be a little bit aware of what your border value is, your night sky conditions. During a substorm, you could probably see the aurora from, I guess the suburbs of Atlanta, but it really helps to be a little bit, further away from lights and under clear and dark skies. I've seen photos of the aurora from Manhattan, though, like during the May storm, it was so bright that they could see it from Brooklyn and Manhattan. I mean, there's images of the Statue of Liberty with aurora behind her. So if it's really bright, you could see it from downtown anywhere, essentially. But for these kind of dim displays, you want to be outside the city. The aurora can look very different depending on the phase of the substorm, depending on where you're at. If you're underneath the auroral oval, the aurora is going to be overhead. If you're further away, it's going to be closer to the horizon. So it'll look very different. I always recommend people, if they're out aurora chasing, just take a smartphone, take a photo of the horizon, the northern horizon for us here in North America, and see what you see, because sometimes it will not look like anything to the eye. Red aurora glow is really common, like I said, because the Earth's curvature actually blocks the green. I just love this little graphic here. This is actually from Aurorasaurus, showing what happens when you're really far away from the auroral oval is that you're only seeing the red tops of the aurora. And I think this is well illustrated in this photo that I actually captured of the aurora from India last year during the May storm. You can see this little red glow. This actually occurred during a substorm, and the auroral oval was very extended, towards the equator. It was very far south, but still almost 1,000 miles away, probably somewhere over like northern Mongolia or something. But because there was a substorm and the aurora was so tall, I was able to see it then from my low latitudes. This was like one of the lowest latitude reports of the aurora from that storm. And I was watching a webcam, of course, and I saw it and I hiked out from my hotel. It's at like 3 a.m., so nobody was up, and we were at this hotel that was like gated, so we had to climb a wall. We had no car, so we just walked through the city. And this is actually like a mountain bike park. There's all this light pollution, but you're able to see it, and that was really, really cool. The aurora will look very different on your camera versus to your eyes. This is just a simulation for my own sort of vision, but it'll differ for everybody. Our vision changes with age as well, and of course is different from person to person. So some people I know just cannot see any color in the aurora, whereas some people can see a lot of color. And cameras don't have those limitations. So even the faintest greens can be picked up with a pixel on a camera sensor. There's some ways you can kind of biohack yourself to see more colors in the aurora, and this is probably most relevant for high latitudes because the aurora is more frequent here. I would say if you're down like in the southern U.S., you just want to see it, so maybe you don't want to ruin your night vision doing this. But if you have a flashlight, you look directly into the light. It sounds stupid. It really does sound dumb, but what will happen is more of your cones, which are the color sensitive photoreceptor cells in your eyes, more of your cones will all of a sudden activate. They need some sort of light to activate. In pitch blackness, they're completely turned off. And all you have are your rods, which are great in low light, but only see in black and white. So if you shine into a bright source of light, this also kind of works with the full moon. You will all of a sudden activate your cones, and they'll stay active for like maybe 10 seconds or something. You're looking in the light, you look away at the sky at the aurora, and you can, like, this is pretty remarkable, but it works. You'll see a lot more color. And, this really works if the aurora's bright too. In Alaska, I always tell people to do this if they're okay ruining their night vision. But you'll see a lot of the greens and the reds that you otherwise wouldn't see. And that's just because more of your cone cells are activated at that time. Now, with the like 3 or 4 minutes left that I have, I'll talk about aurora photography. Um, this is just sort of the bare bones here. What you really want, especially from lower latitudes, you're trying to see the faintest glows of aurora, is a camera with a manual mode where you can set a shutter speed like 10 or 20 seconds. You want a low aperture lens, something that lets in a bunch of light. Not low aperture lens, wide aperture lens, low F number lens. And your ISO, you can set that to whatever to make your photo look good. And of course, shooting manual modes that you have full control over your settings. Auroras can be hard to photograph, though. I'm sure a lot of you do astrophotography. It's kind of nice because, you know, whatever you're shooting is going to be there and it's going to look basically the same night after night after night. If you're a Milky Way photographer, and that was me for, it still is me, although we don't get Milky Way core up in Alaska. But when I was living in North Dakota and Minnesota, I would photograph the Milky Way all the time. And it was so nice because you could go into Stellarium. You could say, okay, I'm going to be here on June 5th. Okay, the Milky Way is going to rise here. It's going to look like this. You dial in your settings. You can do practice shots. You're out in the field. You're just relaxed. Whatever. You're just sort of just going with the flow. But with the Aurora, I mean, the Aurora can change very just crazy amounts of brightness in the matter of minutes. This is, for context, a photo that's way overexposed, but taken at 1.6 seconds, f1.8 and ISO 640. I mean, talk about bright, right? If you're going to take a Milky Way photo with that exposure, it would look basically black. So the Aurora can get really, really bright, especially during substorms. So it's important to be on top of your camera settings. Time lapse is my favorite way to shoot the Aurora. I've been doing a lot more real-time video now, but I cut my teeth doing time lapse photography, which is a beast because I have almost 100 terabytes of Aurora photos on these hard drives in my office right now. So I'm still editing. These were shot in 2022. But it's a great way to show the movement of the Aurora and show that sort of dynamic just behavior that the Aurora has that is so unique. And We all know what a time lapse is. And yeah, why I would shoot a time lapse is that you can A, show the movement of the aurora across the sky, but B, you can set everything up. And if you do it right, you can just walk away and you can let your camera roll and you don't have to worry about catching the best moment because your camera will do that for you. It's a lot nicer of an experience. Some tips is that I tend to record at least 10 seconds of footage at the end, which if you're playing at 24 frames per second is about 240 photos. I always use my lowest F number and I actually shoot an auto ISO. The cameras these days, the meters are really good and the computers are also really good at then adjusting, exposure parameters, the ISO, to accommodate for changes in brightness in your scene. So if you have a really old camera, maybe don't use auto ISO, but instead maybe use like an aperture priority or just underexpose, anticipating a substorm expansion and the aurora getting really bright, but auto ISO has worked for me. And for workflow, I use LR Timelapse and Lightroom Classic combined with Adobe After Effects in this plugin called Neat Video. It works really well, and the denoise in Lightroom now and other raw processors is so good with AI, denoise, and all that stuff. I've been shooting a lot of real-time video of the aurora, and this is really, really fun because it can actually show what it looks like more to the eye. Of course, even in real-time video, cameras still accentuate the colors and things, but you can then see the real-time motion. Time lapses show that motion, but sped up. So a big substorm, if it's really violent, it's just going to flap across the sky in a matter of a few frames. But a real-time video can show the actual true motion of the aurora much better. And there's only a few cameras that can do this. One of those is the Sony a7S III, which is what I own. And you want a really fast lens for this, like f1.8, f1.4. And I tend to prefer shooting during a full moon because that added ambient light just lets me use a lower ISO and just makes the whole image less noisy. These are just some more kind of pointed tips. Of course, if you're down at low latitudes, real-time video is definitely still possible, but you won't be getting necessarily as bright of an aurora because it's more sort of closer to the horizon. But I've seen some great videos of the aurora taken with the Sony a7S III during substorms, like during the May storm and the October storm last year, from down in Arizona, New Mexico, places like that. So it's worth checking out if you have one of these cameras, taking it out with you while you're aurora chasing and seeing what you can get. But if you're going to Alaska, this is great because you can just run around and handhold and take videos of the aurora, and they're perfect for social media and sharing with friends. I have a blog article about recommended gear for aurora photography. And because I'm running a little bit, low on time here, I'll just kind of blast through some show and tell. This is something called Steve, which is a kind of aurora, which maybe you've heard of before. It is really called Steve. It stands for Strong Thermal Emission Velocity Enhancement, and I captured this cool time lapse of a Steve over North Dakota. Steve is typically seen at lower latitudes than the normal aurora, which you can see off here to the right, sort of bubbling away. That's towards the north. In this case, Steve was stretching from east to west. But this is a rare type of aurora, which is associated with this really fast flow of gas in Earth's upper atmosphere, which sort of upends a lot of theories that scientists had before this was discovered back in 2016. And it's now, it literally has its own workshop. There's a Steve workshop happening in Fairbanks next weekend. So I'm actually helping to organize that up here at UAF. We have scientists coming in from all over the world who are all studying this thing, this weird type of aurora, which is called Steve. I just think it's so funny. Like it's so normalized for me right now. But then when I talk to people and I'm like, oh yeah, we're having a Steve workshop, they're like, who's Steve and why does he get his own workshop? And I have to tell people, no, it's actually an aurora. And it was named Steve by these aurora chasers. They thought it was going to be funny. So I just love that scientists have ran with it. Like they're just totally accepting. I showed this display before, but it was that big substorm in Alaska that really kicked things off for me. It was just amazing. Churchill, Manitoba, amazing aurora chasing up there, very remote. These are just some photos. First kind of few sets were from March. This is from September. This is a substorm. So this is what I'm talking about when I say the aurora can get really, really bright and just move all across. This was shot with auto ISO. So the exposure is actually maintained throughout this time lapse, but the actual brightness of the aurora was probably, 4 or 5 fold, from this shot to, let me just pause it to like this shot right here. I mean, the entire ground is lit up green and you could actually see shadows being cast by this particular substorm. And this was the best auroral display I have ever seen up in Fairbanks. These are some highlights from last aurora chasing season. This is up above the Arctic Circle. This was up in Venati, Alaska, where I was helping with the sounding rocket. And here are some highlights. My roommate does aurora tours under me, so we run a little aurora tour business, and we've had some really nice shows and a bunch of surprise proposals and things, and it's been a really fun time. So thanks for your attention. I'll leave this QR code up for just, a few seconds here. You can scan it. And I have an email list where I send out a bunch of, educational Aurora information. If there's a CME coming, I'll send out an alert. My email is vincent@theauroraguide.com. And then this is my final slide where you can download the presentation that I just gave if you're interested. And yeah, looking forward to hearing your questions. Thank you.
You guys have that work?
We're working on it.
We're working on it. I can't get it to
I
green.
got more batteries.
Hang on just a second. We'll take some questions here.
Sure.
Oh, can you hear?
Yeah, I can hear it right now.
Anybody have a question? Yes, sir. Right.
No microphone? No. Okay, I got three quickies. First one is coronal mass ejections. What's the average time it takes them to get to Earth? Second question, as the magnetic field shifts, as the planet's magnetic field shifts, do you guys actually notice over years a change in the location of auroras? And finally, the aurora is just a central focus of the Earth's magnetic field. Is there any increased radiation or health hazard by studying coronas versus the guy down on the equator?
Yeah, great questions. So yeah, I'll answer all three of those. Average transit time of CMEs is typically, 1 to 3 days. I would say the fastest CME ever recorded was about 17 hours. And then the normal solar wind traveling at like 350 kilometers per second, which is like the average speed, is about 4 to 5 days. So yeah, about 1 to 3 days is sort of the average, probably mostly like 3 days. And magnetic field shifting, yeah, so the actual magnetic pole itself wobbles and is moving all over the place. And that's, you'll probably see articles online talking about that. The geomagnetic pole is the dipole approximation of Earth's magnetic pole. So magnets like people are used to are just like a bar magnet, like a dipole field. But in reality, magnets have multiple components. So there might be like a dipole field, which means there's two poles. There might be a quadrupole field, which has four poles. So like Earth's magnetic field is mostly a dipole, but there's some planets out there that have like quadrupole magnetic fields, which means they don't actually have like a north and south pole. There's like these weird configurations. So magnetic pole is like all the components together, and that really does move around. But the auroral ovals are really centered around the dipole field. So there are papers out there that have looked at this and the change of the auroral ovals over the last like 300 to 400 years. And the geomagnetic pole has not moved a whole lot compared to the magnetic pole. So the auroral ovals really haven't changed. And then the question about whether or not you get increased radiation, because the particles that are creating the aurora essentially stop at around 80 miles in altitude, or about 60 to 80 miles in altitude, none of that makes it to the ground. So there's no threat to humans, even in airplanes, if they're, traveling underneath an aurora. Even the particles themselves that create auroras are pretty low energy compared to like what you might get from a cosmic ray.
Thank you.
Another question here.
You mentioned that the auroras are made up of electrons during the solar wind. What do the protons and neutrons do coming from the sun?
Yeah, that's a good question. Yeah, so there's protons, there's electrons, there's neutrals as well. The protons and electrons follow magnetic field lines, so those are the ones that we care about and can really like interact with Earth's magnetic field. And there's this whole sort of cycle of how the energy from the solar wind gets into Earth's magnetosphere and causes the aurora. So, when you're thinking about the actual physics of it, electrons and protons typically, their movements around magnetic field lines are opposite. So when you have oppositely flowing charges, you get currents. So that's how we get these current systems that flow in Earth's atmosphere, like the ionosphere, and also in outer space. We have the ring current, which is sort of like this donut shape, current of, electrons and protons moving oppositely, which which can actually create, currents on the ground. There's all sorts of things going on. So yeah, we mainly care about the electrons because those, just because of the chemistry, can create emissions that we see with our eyes. But there's also proton aurora, and there's protons coming into the atmosphere too, and that creates emissions of aurora that we can't see. So there's actually a hydrogen beta emission, which is typically used to study proton aurora, and there's different like lines, like almost like emission lines, like you might expect from just the spectrum of like any element, that are like the fingerprint of the aurora caused by electrons and protons.
Go ahead. Okay. Vincent, does
Yep.
your manual that you can download have the photography hints and in it?
Yeah. Yep.
Does it cover? I noticed most of your stuff didn't cover like use of cell phones. Do you?
Oh yeah. Yeah, I do. I do have a section on that in the book, in like the ebook about cell phones. What I'll say about that is that it depends on the cell phone. I mean, I just have an iPhone, so for me, it's just I just point it up at the sky and it just does it for me. So, but some phones you have to go into like a manual mode, and there's also apps you can download. I think one of them's called like Nightcap Capture or something like that. I've downloaded that before. That one works for like controlling the settings on your own. So, yeah.
Great presentation.
Yes.
I got a question. Before I forget, Vincent, if you will email me that QR code.
Yes.
Get it posted on our website for those that don't maybe. And, or a link or whatever.
We're also recording this, so it'll be on our YouTube thing.
Oh,
So you
sweet.
can play the YouTube and pause it and photograph it on your home computer. So,
Okay, so we'll have that available on YouTube in a week or so.
yeah.
And my question is, so if I want to come up to Fairbanks, kind of what's the routine? I know
Yeah.
I'll be traveling alone. My wife, I don't believe in go with me. Below about 50 degrees, so too cold. So what's the routine? First of all, the season of it, how many days is it good to plan for, that kind of thing?
Yep. Yeah, I mean, there's the long version and the short version. I'll give you the short version, which is the auroral activity peaks around the equinoxes, and that's especially noticeable at high latitudes. Also, the clearest months are between February and April. So combine those two together, and February to April is the best time to come to Fairbanks to see the aurora. I would come for at least 3 nights. There's a stat that people say that, over 3 nights you have a 90% chance of seeing the aurora, and that's because of clear skies. Since Fairbanks is underneath the auroral oval, there's always aurora happening at night. It's just a matter of if you have clear skies. If you're a photographer, I recommend like a quarter moon or new moon, because that gives you the most dramatic pictures. If you're somebody that stumbles around in the dark, then come during a full moon because you can actually see where you're going. I would hire a guide for at least one night that you're up here, because the first night you get here, you're going to be completely wiped from traveling. People underestimate this. They think they can be Superman and go out till 4 a.m. the night that they come in. That's not going to happen, and you might miss a huge aurora. So I recommend hiring a guide for probably the first night and then trying on your own the second 2 nights. Get a car with four-wheel drive. If you can't drive in the snow, hire a guide or just taxi around and take tours that pick you up from your hotel. Book somewhere that's a little bit far out of town, not too far where it's a hassle to go into Fairbanks, but just 5 or 10 miles east or west is good. And just monitor webcams and cloud cover. Like the night of, predictions are pretty bad, even like a day out here in Fairbanks. But in March, the weather patterns are pretty stable, so there might be a stretch of like 5 or 6 clear nights. I saw the aurora this year in March. How many days are in March? 31. I think I saw it like 26 out of the 31 days. And then the previous year it was like 29. And I mean, that was trying, right? I mean, there were some nights that I had to drive, but that's pretty good as opposed to like now when we're getting a bunch of rain and clouds and snow and stuff. So that's what I would recommend. 3 nights at least, March to or February to April.
But you know, Hot Springs is a good experience too. We did that in 2022.
Nice.
Anybody else? Okay, let's give a nice round of applause.
Yeah.